Though turbulence is not particularly easy to define, it's not hard to find examples. In these, we can find certain common characteristics. One of the most apparent is disorder, as can be seen in this channel flow. The disorder is of such a fundamental nature that the flow never is reproducible in detail, no matter how carefully one attempts to reproduce all the boundary conditions. Although the details are not reproducible, averages over suitably large intervals of space or time may be very well defined and stable. Disorder, then, is a necessary factor in any definition of turbulence. It is not, however, sufficient. Here is a pretty disordered fluid motion, but it would be unwise to include it in turbulence. A wave field like this does very little mixing, and mixing is an essential feature of turbulent motion. The mixing action of turbulence can lead to complete blending if the volume is confined, or to the dilution, which is the only thing that makes pollution like this or this barely tolerable. Another characteristic of turbulence is the presence of vorticity. In a turbulent field, the vorticity is distributed continuously but irregularly and in all three dimensions. So turbulent flow has more than one distinguishing characteristic or symptom. Perhaps we can borrow the word syndrome from pathology and say that we have a defining syndrome or set of symptoms for turbulence. These are disorder, irreproducible in detail, efficient mixing, and vorticity, irregularly distributed in three dimensions. This definition effectively isolates turbulence from various kinds of wave motion. It also eliminates all two-dimensional flows. Something roughly like turbulent motion can exist in two dimensions. Weather systems on a large scale represent nearly two-dimensional flows. However, the characteristics of such flows are in many ways so different that it is perhaps unwise to include them in turbulence. Some flows, like this jet, are clearly turbulent. Others are equally clearly not. What is it that determines whether or not a flow is turbulent? To help answer this question, we'll use this apparatus, which is a version of that used by Hagen over 125 years ago in a study of flow through pipes. In these two tanks, we have two different glycerin-water mixtures. One mixture has viscosity about 3 times that of the other. The valve permits us to obtain any combination of the two mixtures. The fluid is pumped by this constant displacement pump so that the flow rate remains the same no matter how the mixing valve is set. Our pipe begins here. Midway down the pipe, we start a manometer tube which we carry downstream so that we can see the upstream pressure simultaneously with the end of the tube, where the pressure is atmospheric. The manometer reading will give us a measure of the average pressure gradient along the tube. Now we start the pump. The manometer reads about 10 units. Now I change the valve setting to reduce the viscosity. As the low viscosity fluid flows into the pipe, the manometer reading decreases. Once more I change the valve setting to still lower viscosity. But look here. We have increased the pressure difference, which means that we have increased the drag. Let's look at it again. I increase the viscosity, down goes the pressure difference. I decrease it again. Up it goes. Now, let us look at the fluid coming out of the end of this pipe. Notice that the fluid comes out in quite a smooth stream. We have the intermediate viscosity with its corresponding low pressure difference. Now let's go to the lower viscosity with the high pressure gradient. The edges of the stream coming out of the tube have become blurred. If we look at this stream in slow motion, we can see that the blurring is resolved into an irregular motion of the surface. The flow has become turbulent, and the onset of turbulence in the pipe has revealed itself both in the irregular motion of the fluid stream and in the greatly increased drag in the tube. In the early 1880s, Osborne Reynolds did a series of experiments on flow-through tubes and came to the conclusion that the criterion for the onset of turbulence was a dimensionless function of the flow parameters, which has since been called the Reynolds number. There is usually a certain amount of arbitrariness in the definition of a Reynolds number, but for pipe flow, let's take it as the diameter multiplied by the average speed divided by the kinematic viscosity. Although the question is still under investigation, it seems that if the Reynolds number, so defined, is appreciably less than 2,000, the fluid is not turbulent. In this experiment, we have deliberately made the input conditions somewhat abrupt. Turbulence occurs at a Reynolds number not much over 2,000. However, if we improve the entrance conditions by putting a nicely flared funnel at the upstream end, we can delay the transition to turbulence to a much higher Reynolds number. Now we have increased the flow rate and further decreased the viscosity. With very great care, it is possible to push the Reynolds number up as high as nearly 100,000 without turbulence. However, here we can reach only about 8,000. The onset of turbulence depends upon the growth of perturbations because of an instability. For example, at this Reynolds number, the flow alternates between laminar and turbulent modes, apparently randomly, depending, presumably, on some random variations of the perturbations. Prominent in our defining syndrome was the word mixing. What about mixing? Let's modify our experiment by introducing a thin streamer of dye into the flow. Notice that the dye forms a thin filament which maintains its identity with very little change right down the tube. The only mixing is molecular, and the concentration gradients are so small that this process is very slow. This is laminar flow. Now we increase the Reynolds number. At the onset of turbulence, our dye filament seems to explode, and the dye is rapidly mixed across the tube. If we want to, we can regard the increase in pressure difference as a manifestation of mixing too. Mixing of momentum.